Hello and welcome to the course of heat engineering. In this lecture, we will study about the very important concept of fluid mechanics and also relevant to the heat transfer problems, that is boundary layer. So boundary layer is basically a thin region near the solid surface which influence the fluid mechanics and thus the heat transfer very much. So let us first talk about velocity boundary layer, or it is also known as hydrodynamic boundary layer. So let us take a solid surface uh, over which from the left flow is incoming. So because of the virtue of the no slip condition, the velocity of the first layer adjacent to the solid surface will be zero, and the second layer uh, will be retarded by the first layer by the virtue of the fluid property viscosity. So in this way, gradient will set up in the normal direction to the surface, and the velocity which was zero at the solid surface will increase very fastly to the approximately uniform velocity which was incoming from the left. So there exists a velocity gradient, and the point up to which the velocity reach to the uniform velocity value is known as boundary layer thickness. And this boundary layer thickness grow as we move along the x direction, suppose that is from left to right here. So the boundary layer, we can assume that it grows freely in one direction, and inside the boundary layer the velocity component u, that is the velocity in the x direction, where x direction is from left to right here, varies from 0 at the solid surface, that is y equal to 0, to approximately equivalent to the uniform velocity speed capital V at y is equal to delta, and delta is defined as the boundary layer thickness. So we can define the fluid flow over the solid surface. We can divide this fluid flow over the solid surface in two distinct region. The one close to the solid surface where the velocity gradient exists, and outside this region the velocity gradient doesn't exist. So in the boundary layer region, the viscous effect and the velocity changes are significant. So because of this viscosity, the velocity gradient exists, and the effect of viscosity can be felt inside the boundary layer. However, outside the boundary layer, the uh, velocity gradient is zero, and thus the shear stress, uh, which can be calculated by mu del u by del y, becomes zero, as del u by del y is zero. So the effect of viscosity, which was to produce the shear stress among the different fluid layers, is non-existent outside the boundary layer. So the outside of the boundary layer, the flow can be treated as in a rotational flow. The frictional effects are negligible, and the velocity remains constant outside the boundary layer. So boundary layer can also grow to transit to the turbulent. Maybe it is laminar initially, and then it passes through a transition region, and finally it becomes fully developed a turbulent flow inside the boundary layer. So this depends upon various parameters like Reynolds number and surface thickness, etc. Boundary layer parameters. So basically there are three main parameters which are used to characterize the size and scale of the boundary layer. The first is boundary layer thickness, the second is displacement thickness, and the third is momentum thickness. The ratio of these thickness parameters describe the shape of the boundary layer. That will come later into the lecture. We will discuss more about the all of these thicknesses. So, boundary layer definitions and the relation between the boundary layer thickness and displacement thickness. So, as I have told you that the boundary layer thickness is defined as the distance away from the surface where the local velocity reaches to 0.999 of the free stream velocity. That is u at y equal to delta becomes 0.99 of uniform velocity. So it is an arbitrary definition which is widely used in fluid mechanics. Next we will try to define the displacement thickness, and because the viscous forces slow down the boundary layer flow inside the boundary layer, so as a result the certain amount of the mass has been displaced because of the presence of the boundary layer. So if there were not any boundary layer, the mass fluid flow inside the rectangle entering and exiting will be equal, but because of the presence of the viscosity effect and the boundary layer, some of the mass is displaced. So if we imagine that this displaced uniform flow, uh, this displacement away from the uniform flow is characterized by del star. So using the principle of mass conservation, we can say that the flow rate with the uniform velocity will be the same as the flow rate being displaced by the presence of the boundary layer. So based on this concept, we can derive the displacement thickness as given by this formula, that is integration inside the boundary layer of 1 minus u over us dy, where u is the local velocity and us is the free stream velocity. Surface shear stress. So because of the relation between the shear force and velocity gradient, shear stress will act over the surface, which can be given by tau w is equal to mu del u by del y, where mu is the viscosity and del u by del y is the velocity gradient value at y equal to 0, that is at the surface. So if you know the velocity profile u in terms of y coordinate, then we can calculate the shear stress acting on the surface. And similarly, we can define the friction coefficient, where tau s is equal to Cf rho v square by 2. So Cf is a non-dimensional number which is non-dimensionalized by rho v square by 2. Methods to evaluate the convective heat transfer. So first method is the empirical or experimental analysis, in which we use experimental measurement technique in a controlled environment to correlate the heat and mass transfer in terms of some non-dimensional number, for example Reynolds number, Prandtl number, etc. So second approach is theoretical or analytical approach. In the theoretical or analytical approach, we solve the boundary layer equations, fluid mechanics for a particular geometry, and we solve it for theta. Theta denotes the temperature, and when we get the distribution of theta, we can calculate the local Nusselt number. So this local Nusselt number can be used to calculate the local convection coefficient. And by integrating, we can calculate the average convective coefficient over the surface. So exact solutions are possible for simple cases, as we know that the fluid mechanics equation are itself not solvable for a large number of problems. So we approach to the approximate solution using some techniques. So one of these techniques is the boundary layer approximate solution, is the von Karman integral momentum equation. So using von Karman integral momentum equation, we can calculate the boundary layer thickness with respect to the local Reynolds number, and which can be given by del by x equal to 4.64 over under root Reynolds x, where x is the location uh, downstream location. Similarly, we can calculate the shear stress, which can be given in terms of Reynolds number, and thus we can calculate the friction coefficient, which comes to the 0.646 over under root Reynolds x. And then we can integrate this friction coefficient over the entire length to calculate the total friction coefficient on the surface. So by using the boundary layer Blasius exact solution, we can calculate del by del x as 5 by under root Reynolds x and CFX as 0.664 under root Reynolds x, and then we can calculate the average coefficient of friction by integrating the above formula over the entire length of the surface. Next important topic is thermal boundary layer. So we know that the hydrodynamic boundary layers develop because of the viscosity, physical property of the fluid. But the thermal boundary layer develops when a fluid which is flowing over a surface comes into contact with the surface which is at a different temperature. So because of these different temperature of the fluid and solid surface, thermal boundary layer is developed. So the thermal boundary layer is the flow region over the surface in which the temperature variation in the direction normal to the surface is significant. So outside the thermal boundary layer, the temperature variation along the direction normal to the surface is not significant. So the thermal boundary layer thickness del T can be given as where the temperature difference becomes equivalent to the 0.99 of temperature difference between incoming stream and solid temperature. So as I have told you that the thickness of the boundary layer del T is can be defined by this concept that wherever in the normal direction the T minus Ts equals to the 0.99 of T infinity minus Ts, where T is the local temperature at that point. Uh, the another point which is worthy to mention is that the shape of the temperature profile in the thermal boundary layer dictates the convective heat transfer between a solid surface and the fluid flow over it. Because we know that the convective heat transfer coefficient is related to the del T by del Y, that is the temperature gradient at the solid surface. Because at the solid surface the convective heat transfer coefficient must be equal to the conductive heat transfer from the solid. The hydrodynamic and thermal boundary layer is expected to have similar characteristic but it depends upon another parameter like Prandtl number. So we will go later on into it. So if the Prandtl number is very much greater than 1, then the hydrodynamic boundary layer will dominate, and the thermal boundary layer will be inside the hydrodynamic boundary layer. So if the Prandtl number is very greater than 1, very much greater than 1, it means that uh, kinematic viscosity is much greater than thermal diffusivity. For example, oils have such property in which the kinematic viscosity is very greater than from the thermal diffusivity. If the Prandtl number is 1, the both of the boundary layer will coincide, and if the Prandtl number is very less, then the uh, uh, hydrodynamic boundary layer will fall inside the thermal boundary layer. For example, the liquid metal, for which the kinematic viscosity is very low than the thermal diffusivity. So remember that the thermal diffusivity is K by rho C, that is thermal conductance over thermal capacitance. These are the references.